All right, last problem. So we're going to design some propane tanks. Ours are going to be just like the ones that you've seen, not the tanks for your grill, but the tanks out in your yard or on a truck. They're going to be cylindrical with hemispherical ends. And so we're going to go ahead and assume the manufacturing costs that you see on the screen. I think it's accurate that the spherical ends are going to cost more than the cylinder in the middle. I doubt these numbers are accurate, though I don't know what it would really cost. But the point is, we'll work with $5 a square foot and $2 a square foot, and you can easily substitute in the actual numbers. The technique is exactly the same. So we want to find the dimensions, and for us, dimensions is going to be radius and length that will minimize the cost of a tank that will hold exactly 1,000 cubic feet of propane. And so here's the situation. We've got the cylinder, and then we've got the hemispherical ends on either side. You're going to glue on. The radius, of course, needs to be the same so they match up. That'd be bad if they didn't. I'm going to think of it, though, just to make it easier for myself. If I take a half sphere and a half sphere, I put them together, I actually have a whole sphere. So I'm going to think about this as a cylinder, and then I'm going to think about it as a sphere. And even though in the actual manufacturing process, we're going to glue half the sphere here and the other half over there, the volume and the surface area is identical regardless of whether we keep them separate in our minds or glue them together. So we're going to work with this for our setup. So the first thing we should do is write down something about the volume. So we were told that we need to have exactly 1,000 cubic feet of propane in our tank. So I'm going to say 1,000 is equal to the volume of this tank plus the volume of that part, while the volume of a cylinder is just the area of the base times the length or the height. In our case, we're thinking of it as length, so it's going to be what? Pi r squared L plus the volume of the sphere is just 4/3 pi r cubed, so 4 pi r cubed over 3. So that's our volume. This is going to be a constraint equation. The thing that we want to minimize is cost. Let's just write it down in words. The cost is $5 a square foot times the surface area of the sphere plus $2 a square foot times the surface area of the cylinder. Well, now we can actually write down the formulas. So this is $5. The surface area of a sphere is 4 pi r squared plus $2. The surface area of a cylinder is what? The surface area. We just want the outside. We don't care about the end. So it's just going to be the circumference times the length. It's going to be 2 pi r times the length. And we can clean this up a little bit and write this as 20 pi r squared plus 4 pi r L. Now, just like before, when we get to this problem, we can see, hey, there's two variables, r's and l's. This is not good. We want to get everything in terms of one variable. So I'm going to go back up to my constraint, and I need to solve for either r or l. And I want you to realize that you're free to choose in general, but there is a very clear right choice and wrong choice here. And the reason is that it's very difficult to solve for R. You definitely want to solve for L, just because it's easier. It's possible, actually. It would be very hard to solve for R in terms of L. So I should pick a color. So I'm going to solve for L, and I'm going to see that L is going to be 1,000 subtract 4 pi r cubed over 3. And then we're going to need to divide by the coefficient in front of L. So divide by 4 pi r squared. I'm sorry, just pi r squared, not 4 pi r squared. And we can clean this up a little bit. We can write this as 1,000 over pi r squared. Nice, we can cancel some stuff on this side. So I get minus 4r over 3. So that's what L is. And so I'm going to be able to take that now and plug that into my cost function. So my cost function is going to be 20 pi r squared plus 4 pi r times L. Well, we now know L is this guy, so it's going to be times 1,000 over pi r squared minus 4r over 3. And now we're just going to do some algebra, combine everything, clean everything up. So this is 20 pi r squared plus, let's see, we can cancel a pi and an r, and so we get 4,000 over r. And then minus, pushing everything through, we get a 16 pi r squared thirds. Notice that there's a pi r squared here and a pi r squared there, so we can combine these two as 20 minus 16 thirds is the same as, what, 44 thirds. So my final cost, I'm going to now view it as a function of r, is 44 pi thirds times r squared plus 4,000 over r. So at this point, you're ready to take derivatives now and try and figure out what's happening. I don't know that we noticed at the beginning, we probably should have, but it's sort of clear that your r and your L both have to be greater than 0. You really can't have a negative radius or negative length. So here it should also be clear that r is bigger than 0. So let's compute our derivatives and see what happens. We're going to get just 88 pi thirds times r, easy enough, minus now 4,000 over r squared. I'm just using the power rule, make sure you're comfortable with that. I'm interested in where is the first derivative, 0 or undefined. It's undefined at 0, but I have to be bigger than 0, so I'm going to ignore that one. I'm just going to solve where is the first derivative equal to 0, and so I'm going to come up with 88 pi r over 3 equals 4,000 over r squared. I'm going to cross multiply, and I'm going to get, what, 88 pi r cubed is 12,000. Just about got my hands on r, so r cubed is 12,000 over 88 pi, and you can cancel it too if you want. I went ahead and just realized that r is the cubed root of 12,000 over 88 pi, and then I simplified this. I plugged it in and I got roughly 3.51439. Now, here's what I see many Calc 1 students do, is they've worked all this out, and they know that I'm giving them a problem that is going to have a solution to it. So they say, okay, well, that's going to minimize cost. That's the radius that will minimize cost. And then they'll figure out the corresponding length, and they'll be done. And the answer is correct. That's true. But let's just imagine with me for a moment that you're working for a company and your boss tasks you with this problem. He's going to design some tanks, and you do this, and you say, okay, boss, this is, that's the answer that is going to give you minimal cost. That's the radius. Here's the length, blah, 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 blah. And so the boss goes and he orders maybe 1,000 of these tanks, and 2 weeks later you realize that actually that wasn't the minimum, that you missed something. And you can just imagine the situation. It would be horrible, and you could easily lose your job. So we want to confirm that this really is an absolute minimum. Don't just assume it is because you wanted it to be. So how do we do that? Well, we're just going to make a quick number line. Whoops, get to my pen here. We're going to make a quick number line. The number line is for the derivative. So this is for c prime of r. We know we have to be bigger than 0. Here's our 3.5, roughly, whatever. And I just want you to plug in something bigger than 3.5 into c prime. You'll need to plug in, use a calculator, and when you do that, you're going to get a positive. And when you come over here on the other side between 0 and 3.5, you're going to get a negative. And so the point is your function is decreasing, 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 and then it's increasing forever on. And so now you know that that's a local min, but it's also an absolute min because you're in the function c is increasing everywhere beyond your critical point because C prime is positive beyond there. So now you know, just looking at the number line tells you. So you can say, thus, the C of R has an absolute minimum at R, and we're going to go ahead and say roughly 3.51439. And then we should answer the actual question, i.e. R equals, let's again say roughly 3.51439. You can go back now into your formula for L and plug in R and solve. I won't work out the details, but I'll tell you what you get. You're going to get L equals 21.0863. These will give volume of 1,000 cubic feet with the minimal cost desired. So that's a nice applied problem, and that's how you can use calculus to solve it. So I'll end here. Homework is going to be due tomorrow, which I'm posting these videos on Monday, so tomorrow evening at midnight. Ciao.